Hello and welcome back to Pre-Calculus. You should have pre-printed notes for this section, and I have a packet that you have here that has the explanations for all of these functions. You might want to write down as I go through domain and range though. We're going to be talking this section about the 12 basic functions. These are the mother functions, I'm telling you. And the reason we're going to be talking about them is because they're used over and over again. We're going to start out talking about the different types, and I want you to be able to tell the shape of the function and how it relates to the equation of the function. For example, what does an x squared function look like? If you see a humpty-hump one, what degree would that be? You need to have an idea in your mind how the equation of the function, the algebra expression of the function, relates to what the graph looks like. We're going to be talking about domain and range. So the first part of the notes, you should have the stapled packet that have them all listed, and I thought this would be a good reference as you go through the homework and do the application problems. I am also going to give you a pop quiz. Well, it's not really a pop quiz because I'm telling you about it, where you have to match the equation with the graph. That is going to be a quiz you're going to have. It's going to be worth 20 points. And the ones you see on here are what I call the mother function. They could be shifted around or flipped upside down, but these ones are the mother function. So this is called the identity function in your book, but it is just a linear function. It's a linear model. If you look at the last page of your notes, I show you over here how each one is used in the real world, and why we study these is to model situations and make predictions. So over here in your notes, it lists all the applications of these functions. This is a line y equal ax plus b, but the mother function is just y equals x. What would be the domain on this function? If you recall, you look left to right. Are all the x's included? Is there a point on the graph for every x value? There is. So the domain here would be from negative infinity to positive infinity. Or in words, you would write all real numbers. The range is going to be the same. As a hint, almost all lines have domain and range to be negative and positive infinity. There are only two exceptions. A horizontal line would have a domain of all real numbers, negative infinity to positive infinity. But if you think, a horizontal line would only have one y output, so the range would be just one y value. Conversely, a vertical line would have all y values and only one x value. So the domain would be one x value and the range would be all real numbers. But other than those two lines, if it's not vertical and it's not horizontal, if it's a line, domain and range is all real numbers. The squaring function, I'm hoping you are familiar with this. We did a lot with quadratics in Algebra 2. It's a parabola. It is symmetric about the y-axis. If you look left to right, I can get in a y value for each x on each side, so the domain is going to be all reals. But the range, if you notice the graph, when I look up and down, it goes just from 0 on up. So the range for this one is from 0 to positive infinity. So when you're looking at a quadratic function, you always need to check the range. Sometimes they'll be facing up, smiley face like this. Sometimes they will be facing down, concave down. And you'll have to determine what the range is. But to me, that's an easy way to look at it. Be aware that the range on your parabola is going to be affected. It's not going to be all real numbers. The cubing function, that's a cubic function. If you look left to right, you've got all x's represented. So the domain for this guy is going to be all reals, negative infinity to positive infinity. And the range is going to be the same. So this can be true for all of the odd-powered polynomials. You're usually going to have that, unless you have some special cases. Reciprocal function, this is where x is in the denominator. Now if you look there, there is something that if I put it in for x, it's going to make that function undefined, and that something is 0. So the x cannot equal 0 because you cannot have 0 in the denominator. You'll have to check out the denominators of these types of functions, these rational functions, to figure out what the domain is. If I look left to right, as I go, I've got graph, 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 no graph. It jumps over the 0, and then I've got the blue graph continuing on this way. The range likewise jumps over the 0. If I look up and down, my range would be would be the same thing, negative infinity to 0, union 0 to positive infinity, with the rounded parentheses around there, because it skips over the 0 if I go up and down. There's no y value at 0. Square root function. What you should notice about this function is it increases as it goes to the far right. And notice you cannot put a negative in there, which you know you can't put a negative under the square root. It is a non-real number. And you don't have any y values that are 0. So your domain is going to be x greater than or equal to 0, because you can put 0 in there. Square root of 0 is 0. And your range, if you go out far enough, you'll get all your positive y values. So your range would be y greater than or equal to 0, or 0 to positive infinity as well. The exponential function increases as you go from negative infinity to positive infinity, and it gets very big very fast, and it has this kind of backwards hockey stick look to it. This e to the x, e is just like pi. It's called the natural e. If I go from the far left all the way to the right, I can put any value in for x, and I'm going to get a y value out. But if you notice, this function does not go below the x-axis, so there's no negative y values, and likewise there's no 0. It's going to get closer and closer to 0 without touching. Natural log cabin. It's a calculus joke. If you get there, I'll say, what's the antiderivative of 1 over cabin decabin? It'll be natural log cabin. I always think of that when I see this natural log. It's the inverse. If you compare the natural logarithm function and e to the x, they're inverses of each other. They're flipped over the line y equals x. And this one, the domain would be from, you can't have a 0 to put in for x. So you'd have to say it's greater than 0, and it goes all the way to the right. So the domain is going to be x greater than 0. The sine function, yes, we did this last semester with the trig, and hopefully you know it's what the sine wave looks like. We did a lot of stuff with that. Domain, it's going to be negative infinity to infinity, and you should know that the range is from negative 1 to 1. So the range starts and stops there, and that the domain is negative infinity to infinity. Same for the cosine function. You should be familiar with those. The difference is this one is symmetric. It's an even function, and the sine is an odd function. Absolute value, you did a lot of this with algebra and algebra 2, and it is a symmetric function. It would be even. Domain would be all reals, but the range, the output, would only be positive numbers, so it would be from 0 to positive infinity. This might be a new one for you. It's called the greatest integer function. Do you notice how they have stair steps here? The stair steps, it steps all the way up. It is missing the values of y between 0 and 1. It only gives output of integers. So in other words, the output is negative 1, 0, 1, 2, 3, 4, and so on. You can put any value in for x, but it's going to return the greatest integer. So that's a strange one, but you might ask, where would an application be for this? Postal rates, and there used to be phone bills. They would bill a certain way with a greatest integer function. Range is a set of integers, which is called z. This is called the logistic function, and something interesting about this one is it models how a rumor is spread, how quickly it's spread, the growth rate of a gossip, how it's spread. And it's 1 divided by 1 plus e to the negative x. There's two horizontal asymptotes at 1, y equal 1, and y equals 0. So y is between 0 and 1, not including 0 and 1. Let's look for some domains. 9 of the functions have domain, the set of all real numbers. Which 3 do not? Well, you have to think, what's eliminated out of a domain? You can't divide by 0, and you can't have a negative under a square root. So that's going to clue you in. Square root function, because the domain is greater than or equal to 0. ln function, because we cannot put a 0 in there. It's the inverse of e to the x. And the 1 over x, where we cannot divide by 0. So they're looking at the different domains, making you realize the difference between these different functions. So domain for this one is going to be negative infinity to 0, union 0 to positive infinity. One of the functions has domain all real numbers except 0, Which function is it, and why isn't 0 in its domain? Well, that's the 1 over x function that we just saw. And the reason is because putting a 0 in for x makes a 0 in the denominator, which makes the function undefined and creates a vertical asymptote at x equals 0. Which two functions have no negative numbers in their domain? That would have to be one of them is going to be the square root, and the other one is going to have to be the ln of x. Those two do not have any negative numbers. You can look at the picture and see that you don't have any values on your graph for the x's that are negative. Square root function is defined at 0, so it is not. Example 2, and hopefully you're on your sheet. There's a note sheet for these. Which of the 12 functions are even symmetric about the y-axis? X squared, you could fold it along the y-axis, the cosine graph, and the absolute value graph. Those would be the 3 that are even. Looking at the graph, we can tell a lot of things. Which interval the function is increasing or decreasing? Is it even, odd, or neither? Does the function have any extrema? And how does the graph relate to the graph of the basic function y equal x squared? We're also going to find the function's domain and range. So they're saying from this graph you can get a lot of information. So if we look at this one, if we graph this, the opposite of x squared minus 1, just seeing that it's a second degree equation, it's a quadratic, clues me in that it is a parabola. And the first question, it's going to be increasing all the way up to the maximum. So as I look left to right, this function goes uphill all the way to its vertex. Vertex is 0, negative 1. So remember, this is the interval on your x values. It's symmetric with respect to the y-axis but not the x-axis, so the function is even. It also has a maximum value of negative 1 at x equals 0 because that's the top of the hill. The graph is the graph of y equal x squared reflected over the x-axis and translated 1 down. So x squared is its mother, and it's moved around a little bit. What's the function's domain and range? Easy to find on the graph. You can put any value in for x, but y is strictly less than negative 1. So the domain is from negative infinity to infinity, and the range is from negative infinity to negative 1. We're going to do piecewise functions tomorrow. That's it for now.